In this lesson, we'll be looking at chemical equations. Chemical equation is simply a paper representation of what happens in a reaction vessel. Usually, chemical reaction occur between substances. And when such reaction occur, there's usually a formation of a new substance. The substance that react together are called reactants, while the substance that is formed is called or are called products. The reactants are usually written on the left-hand side, while the products are written on the right-hand side. Then we use an arrowhead to link the reactants to the product, showing that reactants combine together chemically to give the product. So this paper representation of what happens inside the reaction vessel is known as a chemical equation. So for example, you may have a hypothetical element A reacting with another hypothetical element B to give us hypothetical element or compound C and D. So A and B here are reactants, while C and D are products. Now, when these reactions are written, sometimes the equation will not be balanced. Now, what does it mean? You may have maybe A2 as an element reacting with B1 as an element to give us an atom of A, B plus C. In this case, on the left-hand side, we have two atoms of A. This is just hypothetical. There's no element A. Then on the right-hand side, we have only one. That shows atoms have been destroyed because on the left you have two, but on the right you have only one of A. And the law of conservation of matter says that matter is neither created nor destroyed. So as long as the number of atoms on the left do not agree with the number of atoms on the right, it means the equation is not balanced. It implies atoms have been created or destroyed. So for that reason, whenever a chemical equation is written, we do atom count to ensure that the number of atoms on the left is equal to the number of atoms on the right. We make them equal. And that process of making them equal is what we call balancing of chemical equation. Now, how do we balance a chemical equation? Like I said, we do atom count and then make adjustments to the number of moles of each of the components or elements or compound or radicals. So my approach in balancing a chemical equation, first of all, let's start with the most basic equation, which is hydrogen combining with oxygen to give us water, because the formula of water is H2O. This is hydrogen gas combining with oxygen gas to give us water. And you see that the equation is not balanced because on the left-hand side, we have two atoms of hydrogen, two atoms of oxygen. But on the right-hand side, yeah, hydrogen is okay. We have two atoms here also. But oxygen, we have only one. That means oxygen have been destroyed. But the law of conservation of mass says atom or matter is neither created nor destroyed. So to respect that law, we need to balance this equation. And my approach is to start from where I have odd number of atoms. Then convert that odd number of atoms by placing a 2. Of course, you can't place a 2 here, it's wrong. You can't change the number of atoms. You can only change the number of moles. So we place a 2 here in front of H2O to make it 2 moles of water. And now I will place a 2 there. That 2 affects both hydrogen and oxygen, which means now we have a total of 4 hydrogen on the right hand side, but we have 2 on the left hand side. Oxygen, however, is balanced because these 2 here affect oxygen, meaning there are now 2 oxygen on the right hand side and also 2 oxygen on the left hand side. But putting a 2 here have changed the number of hydrogen, so we need to put a 2 here also to balance the number of hydrogen on both sides. So this now is 4 hydrogen on the left, 4 hydrogen on the right, 2 oxygen on the left, 2 oxygen on the right. So the equation is finally balanced. Now we can only write a chemical equation for a reaction that occurs If a reaction does not occur, you cannot write the chemical equation for it. For example, see this thing here, Cu plus H2 HCl, giving us CuCl2 plus H2. This equation does not exist because copper does not react with hydrochloric acid. So I decided to write it because I want to make a point there. Yeah, even though looking at it, it seems correct, but it doesn't exist. So the point here is for a reaction that doesn't exist, a reaction that doesn't occur, we cannot use a chemical equation to represent it. So you can only write a chemical equation for an equation that is physical. So balancing of chemical equation is a trial and error kind of trial and error in the sense that if you place a number that is changing the number of moles of the reactant and the product, you use a particular number, you do atom count. If the number on the left does not agree with the number on the right, then you have to change the number again. You continue doing that until the numbers finally agree together. So we have an example here. Say write a chemical equation for the combustion of ammonia gas in air. Any combustion reaction has to do with the reaction between the substance in question and oxygen. But without oxygen, burning cannot happen. Combustion means burning. So when you see combustion reaction, we are talking about a reaction between that substance and oxygen. So now the question says write the chemical equation for the combustion of ammonia gas in air. So ammonia is NH3, while oxygen is O2. So reacting the two of them together, this will give us nitrogen oxide, water. Now, doing atom count, we see that the number of atoms on the left and on the right are not the same. On the left, we have one nitrogen. On the right, also one nitrogen. So nitrogen is okay. But hydrogen on the left, we have three. On the right, we have two. That means hydrogen is not balanced. Then oxygen on the left, we have two. On the right, we also have two. Let's start by balancing this hydrogen. I'll put a 2 here. Like I said, it's a trial and error. You place a 2 and do atom count. If it doesn't work, change it to another number. And notice that it's the number of moles that I am changing, not this number in front. This number in front here is number of atoms. You cannot change that in balancing an equation. You can only change the number of moles. So placing a 2 here now makes nitrogen 2, while hydrogen is 6. That is 2 times 3. And to balance that, if we put 2 here also, because I have two nitrogen on the left, so I need to balance the nitrogen on the right also by placing a 2 there. So now that makes nitrogen 2, 2 on both sides. And what about hydrogen? Hydrogen on the left is 6. So to balance it on the right, if we put a 3 here, that makes oxygen on the right to be, these three affect both hydrogen and oxygen. So 3 oxygen plus 2 oxygen, that is 5. But there's no way we can turn this one on the left to 5, which means using a 2 will not work for us here. So we need to change it to another number. Let's change to another number. What about placing a 3 here? Placing a 3 here will still make hydrogen to be an odd number. Like I said, my approach is to try and convert. I have been using that approach for a very long time and I discovered that it always works for me. I start by converting anywhere I have odd number of atoms. So if I place a 3 here, I will still have odd number of hydrogen. So let me move on to 4 right away. If I place a 4 there, that will make nitrogen 4, hydrogen 12. That is 4 times 3. So if I place a 4 here also to balance the nitrogen, that makes oxygen here 4 plus this one here, which is 7. Then how many hydrogen do I have here? I have 12 altogether on the left hand side. That is 4 times 3. To balance it on the right hand side, I can put a 6 here. So that 6 times 2 is 12. And now this 6 also affects this oxygen, meaning I have 6 oxygen here and 4 oxygen here, so that the total number of oxygen on the right hand side is 10. To balance it on the left, I can place a 5 here, so that the equation is finally balanced. Let's do atom count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 4 nitrogen on the left, 4 nitrogen on the right, 12 hydrogen on the left, that is 4 times 3, 12 hydrogen on the right, that is 6 times 2. Then 10 oxygen on the left, 4 plus 6, also 10. So the equation is balanced. And I have another example here. So when steam is passed over red hot iron, hydrogen gas and an oxide of iron are formed. Balance the equation. We have written the equation here for us, but it's unbalanced. We have to balance it. That is Fe, Fe is iron plus H2O is water, giving us iron oxide, that is iron 3 oxide, iron oxide plus hydrogen gas. So we have to balance the equation. We start by doing atom count. On the left, we have only one atom of iron, but on the right, we have 3 atoms of iron. Then hydrogen on the left is 2, on the right is also 2. Oxygen on the left is 1, on the right is 4. To balance this, let's start by putting a 3 here to balance the iron. Then we need to balance the oxygen also by putting a 4 here. If I put a 4 here, this 4 affects hydrogen also. But on the right hand side, I have only 2 hydrogen. I need to put a 2 here. And that balances the equation. Let's do atom count again. 3 iron on the left, 3 iron on the right. 8 hydrogen on the left, 8, I put it 2 instead of a 4, sorry. It's supposed to be 4. This hydrogen here is supposed to be 4. And this is 4. Okay, so we do atom count again. 3 iron on the left, 3 iron on the right. 8 hydrogen on the left, that is 4 times 2. 8 hydrogen on the right, 4 times 2 also. 4 oxygen on the left, 4 oxygen on the right. And so the equation is balanced. And the next one says write a balanced chemical equation for the combustion of ethane in oxygen, a product of the reaction of carbon 4 oxide and water. Ethane is C2H6. Whenever any organic compound bonds in oxygen, it gives carbon dioxide and water to CO2 plus H2. All of them are gases. Now doing atom count, on the left hand side we have 2 carbon, on the right we have only 1. On the left hand side we have 6 hydrogen, on the right we have 2. On the left we have 2 oxygen, on the right we have 3. So let's start by balancing the number of oxygen. Now carbon is 2 here, on this side we have 1. So if I put a 2 here to balance carbon, that makes my oxygen to be 4. 4 plus 1, which is 5. But on the left hand side, I have 2. There's no way I can convert this to a 5. So let's, balance hydrogen also. Hydrogen on the left is 6, but on the right is 2. So if I place a 3 here to balance hydrogen, that makes oxygen to be 3 also here. Then 3 plus this 4 here, that is 2 times 2, 4. That is 7, which does not agree with what we have on the left hand side. There's no way you can convert this to 7. So I will turn this to an even number of atoms. Instead of using 3, then we use 4 there and see. It doesn't work. I will change it to another one. That is how we do a trial and error. So 4, that means hydrogen to be 8. But on the left hand side, hydrogen is only 6. Okay, let's see whether oxygen is balanced. That is 4 oxygen here plus 4 oxygen here. That is 8 altogether. But hydrogen is not balanced. On the right, we have 8 hydrogen. On the left, we have only 6. And that means that will not work again. So let's try another number. We need to remove all of this. Okay. Let's start by converting this odd number of oxygen to even number of oxygen and see what we are going to have. We have used a 4 there already. It doesn't work. So let me use a 6 there and see. Now that makes oxygen 6 plus these two 8 altogether. So that if I place a 4 here, that is 8, 8. Oxygen is balanced, but carbon, I have 2 here, I have 1 here. So if I place a 2 here to balance the carbon, then that makes oxygen on the right hand side to be 2 times 2, 4, plus this 6 here, 10, which means this 4 here will not work. I need to place a 5 here for oxygen, because on the right I have 10 atoms of oxygen. I know the number to put directly, I'm just showing you as a guide so that you know that it is trial and error. It's not there's no fixed rule of doing this. You try one number, it doesn't work. Change it to another number until you get the perfect one, guys. And at each stage, you have to be doing your atom count. So now let's do the atom count again and see. Carbon 2 on the left, 2 on the right. Hydrogen 6 on the left, but we have 12 on the right, which means hydrogen is not balanced. Oxygen is 10 on the left, also 10 on the right. Because these two affect oxygen also, that is 2 times 2, 4. Then this 6 also affect oxygen. 6 times 1, 6. That means 6 plus 4, 10. But hydrogen is not yet balanced. We have 12 hydrogen on the right hand side, but 6 on the left hand side. So if we put 2 here to make hydrogen 12 also, that makes carbon to be 4. But on the right hand side, I have only 2 carbon there. So let's remove this and place a 4 there to balance the carbon. But that affects oxygen now because 4 times 2 is 8. Then 8 plus this 6 here, that is 14. So to balance the oxygen, we need to put 7 here instead of 5. So and now it is balanced. Let's do atom count again. 2 times 2 for carbon, that is 4. 4 carbon also on the right hand side. Then 2 times 6 for hydrogen, that is 12. Then 6 times 2 also here, that is 12. And what is oxygen? 7 times 2, 14. On the right hand side, you have 4 here times 2 here. 4 times 2 there is 8. Then 6 times 1 here, 6. 8 plus 6 is 14. So the equation is balanced. The importance of balancing a chemical equation. Why do we have to balance a chemical equation? The following information are provided by a balanced chemical equation. It tells us the reactants and the products involved in the reaction. So in this case, the reactants are that's for this very reaction, and they are referring for this to this reaction. As in this reaction, what are the reactants? The reactants are HCl and CaCO3. That is hydrochloric acid and calcium carbonate. Why the products are calcium chloride, carbon 4 oxide, and water. So a balanced chemical equation tells us the products, the reactants, and the products involved. It also tells us the individual elements and radicals involved. In this case, the elements are hydrogen, chlorine, calcium, carbon, oxygen, and the radical is this triisocarbonate 4. As triisocarbonate 4 is a radical. It behaves as a single unit, even though it's a group of atoms. Then it also tells us it gives us the mental picture of the movement of the elements and radicals during the reaction. You can see we are pointing an arrow from the reactant to the product. That means these items on the left-hand side are the one that combine together to give these items on the right-hand side. It's a mental picture of how this movement occur, the element and the radicals. Then it also tells us the stoichiometry of the reaction. Stoichiometry means the relationship between the amount of the reactant and the product. That is in terms of their mole ratio and the mass ratio of the reactants and products involved. These ratios are easily calculated since the numerical coefficient of the balance equation represents the number of moles of reactants and products. So the direction of the reaction and whether the reaction is reversible. As a chemical equation tells us what the direction of the reaction and also whether the equation is reversible. Equation that has only one arrow pointing to the right hand side means it is irreversible. So for example, A plus B giving us C plus D. This is an irreversible reaction. On the other hand, when you see an equation that has two arrows, one pointing forward, the other one pointing backward, that is a reversible reaction. It can occur both forward and backward. And also, most reaction tells us the state of the matter in which the substance are present. For example, this equation here, you can see the states are indicated by the symbol X. S stands for solid, and L for liquid, Q for aqueous. Aqueous means the thing is inside water. The solid plus water, giving us a solution. Solute plus water, giving us a solution. Now let's assume this solution is represented with a formula AB. So to indicate the state of this solution, we put aqueous to show that it is dissolved in water. Y S stands for solid, L for liquid, and G for gas. So a balanced chemical equation also tells us the state of matter that reacts, whether they are substance, they are solid, liquid, gases, or in aqueous solution. So for this reaction that is given to us here, which is HCl, HCl is of course aqueous, dilute with water, plus calcium carbonate. Calcium carbonate is solid, giving us calcium chloride. This is aqueous now, since you already put it inside this, and this is diluted with water. So now put a solid inside a diluted solution, then whatever is formed within that solution. So this calcium chloride now is aqueous because it's inside the solution. Yeah, it is a substance that is formed, but within that solution, the plus carbon dioxide. Carbon dioxide is gas, so it's going to come out of the solution. The same thing with water. Water is liquid, it still remains in the solution. H2O, the liquid. So here, HCl is aqueous, meaning it's dissolved in water. While calcium carbonate is solid, calcium chloride is aqueous, also in water. That is inside the solution. And I have a vessel here. Inside this vessel, I have what? Dilute HCl. Then I put calcium carbonate, which is a solid, inside this dilute HCl. A reaction is going to occur inside the dilute HCl to form this very product here, which is calcium chloride. The calcium chloride will be formed within this container. And in this container, you have water there. So that is why it is aqueous. Okay. Then carbon dioxide is a gas. As the reaction occurs inside this vessel, the gas will come out. It's coming out. We need to indicate it as gas. Then the water is within this vessel also as the reaction occurs. And from the above balance equation, we can obtain the following geometric relationship. We have two modes of, okay, let's first of all balance the equation before I talk about that. I have already messed it up there. Let me rewrite it again. So HCl aqueous plus CaCO3 solid, giving us CaCl2, which is aqueous also, plus carbon dioxide, which is gas, plus H2O, which is liquid. Now, is this equation balanced? No, it's not balanced. On the left-hand side, we have one hydrogen. On the right-hand side, we have two hydrogen. Also, on the left-hand side, we have one chlorine, but on the right-hand side, we have two. So let's put two here to balance the hydrogen and the chlorine. What about calcium? Calcium is one here, also one here, so it's balanced. Carbonate, I see CO3, carbon one also. Then oxygen 3, oxygen 2 plus 1 here, 3. So the equation is balanced. So from this balanced equation, we can see that 2 moles of HCl react with 1 mole of calcium carbonate, and also 1 mole of calcium carbonate produces 1 mole of carbon dioxide. Why do we specify this, that it is this that produces this? Because this CO2 comes out of this radical here, CO3. That is why it is specific there that 1 mole of calcium carbonate produces 1 mole of CO2. And then 100 gram of calcium carbonate produces 44 gram of CO2. Where did you get that 100 gram from? That is a molar mass of CaCO3. We call that molar mass is obtained by adding the masses of all the component elements. So calcium is 40, carbon is 12, oxygen is 16, but there are 3 atoms of oxygen there. So 16 times 3, which is 48. That means 40 plus 12 plus 48 is of course 100. The 100 gram of calcium carbonate give us 44 gram of carbon dioxide. Where is the 44 coming from? The molar mass of CO2. Carbon is 12 and oxygen is 16. There are 2 atoms, that is 16 times 2, which is 12 plus 48. 12 plus 32, which is 44. Also, 100 gram of calcium carbonate reacts with 73 gram of HCl to produce 111 gram of calcium carbonate. That is a stoichiometry we are talking about now. When you say stoichiometry, We're talking about the mass the mole to mass ratio. So 100 gram of calcium carbonate reacts with 73 gram of HCl to produce a 111 gram of calcium carbonate, calcium chloride rather. This 73 gram again is molar mass of HCl. HCl, the mass of hydrogen is 1, that of chlorine is 35.5. Then 1 plus 35.5 is 36.5. Now you ask, where is the 73 coming from then? When we balance the equation, you see that it is 2 mole of HCl that reacted. So this 36.5 times 2 is 73 gram. So in other words, 100 gram of CaCO3 reacts with 73 gram of HCl to produce 111 gram of calcium chloride. So all of this information are provided by a balanced chemical equation. What about the information that are not provided? A balanced chemical equation does not tell us the speed of the reaction, whether the reaction is slow or fast, whether it needs a catalyst or not. It also does not tell us the heat changes during the chemical reaction and also the colors of the reactant and products. We don't know, we only know their states, whether solid, liquid, gas, or aqueous. So now this information provided by a balanced chemical equation are important in several calculations, as we are going to see shortly. So the subtopic here said calculations from balanced chemical equations. From an equation, we can calculate the amount of reactants and products formed. These are important in chemical industries that are engaged in the manufacture of basic chemicals. These are produced after this type of calculations we are doing now. So the first one here says the equation for the formation of water is 2H2 gas plus O2 gas, giving us 2H2O gas. Calculate the number of moles of oxygen required to yield 6 moles of water. So H2O is hydrogen gas plus oxygen gas, giving us water. To balance the equation, we put a 2 here and a 2 here. And now the question is, well, you calculate the number of moles of oxygen required to yield 6 moles of water. From this balance equation, 1 mole of oxygen yield 2 moles of water. That is the essence of balancing an equation. So from the above equation, the balance equation, 1 mole of oxygen yield 2 moles of water. That means X mole of oxygen will give us 6 moles of water. Since the question says we should calculate the number of moles of oxygen required to use 6 moles of water. So let that number be X. That is the meaning of X mole of oxygen yield 6 moles of water. So that by proportion, if we cross multiply this, X times 2 is 2X. Then 1 times 6 is 6. So that 2X, I just cross multiply, equal to 6, meaning X equal to 6 divided by 2, which is 3 moles. So 3 moles of oxygen are needed to produce 6 moles of water. The next example says calculate the mass of lead which will be obtained by heating 35.25 gram of tri-lead tetroxide in a stream of hydrogen and the mass of water formed at the same time. Okay, so the question is, they calculate what the mass of lead which will be obtained by heating 35.25 gram of tri-lead tetroxide. Tri-lead tetroxide, that is Pb3O4, that is tri-lead tetroxide. Now, when it is heated in a stream of hydrogen, that means it's going to be a reaction between tri-lead tetroxide and hydrogen. So plus hydrogen gas, that will give us lead plus water. And is the equation balanced? No. Let's indicate their state. Lead is solid, then water, the water that is formed is gaseous water, that is steam. And nitrogen is gas also. Then tri-lead tetroxide is solid. Now, on the left-hand side, we have 3 atoms of lead. On the right-hand side, we have 1. So let's start by balancing the lead. I place a 3 there. Then oxygen on the left-hand side, we have 4. On the right-hand side, we have only 1. Let's balance that by placing a 4 there. But that 4 affects hydrogen, making hydrogen to be 8. But on the left-hand side, we have only 2. So we also place it 4 here, and that balances the equation. And the question says we should calculate what? The mass of lead which would be obtained by heating 35.25 gram of dry lead tetraoxide. First of all, we need to get the molar mass of all this. And the question borders on trilead tetraoxide and the lead itself. So we need to get the molar mass of trilead tetraoxide, then get the molar mass of lead in this very reaction. So from the reaction molar mass of trilead tetraoxide is equal to the mass of lead is 207, but you have 3 atoms of lead here. So 207 times 3 plus mass of oxygen is 16. You have 4 atoms of oxygen there. That will be 207 times 3, 621, plus 16 times 4 is 64. And 621 plus 64 is 685. That's 685 gram molar mass. Then we also calculate the mass of lead formed in this very reaction. The molar mass, I call it molar mass. That is actually more than molar mass because I have 3 moles there. Let me call it mass of 3 moles. Mass of 3 moles lead, because I'm referring to this now. Lead is equal to 3 times 207. 3 times 207. Okay, 7 here already. That's 621. 207, 621. That means in this reaction, 685 gram of trilead tetraoxide give us 621 gram of lead. Then what would this 35.25 gram give us? Yes, it's 685 gram trilead tetraoxide give us 621 gram of lead. What does that mean? We calculated the molar mass of trilead tetraoxide in this reaction. We have 685 gram. Then we calculate the mass of these 3 moles of lead that is formed as a result of the reaction. We got 621 gram. That means the mass here produced 621 gram of lead. But what we are hitting in this reaction is 35.25. These values we have here are the mass based on this balanced chemical equation. But what you did, your experiment is using 35.25 gram of trilead tetraoxide. What would be the mass of lead produced in that case? So 35.25 gram of trilead tetraoxide will give, let it be X. So by proportion, we cross multiply this, X will multiply 685, while 35.25 multiply 621. So 685, 385x is equal to 32.25, 335, rather. 35.25 times 621. So dividing both sides by 685, x equal to 35.25 times 621 divided by 685. 35.25 times 621 and divided by 685. That is 31.95. So the mass of lead obtained from heating 35.25 gram of dry lead tetraoxide is 31.95. Then the second part of the question says, and the mass of water formed at the same time. The mass of water formed at the same time. From this balance equation, what is the mass of water? Mass of 4 moles of water. 4 moles of water is equal to 4 times. Hydrogen, the mass is 1, but there are 2 atoms there. That is 1 times 2, which is 2, plus oxygen, the mass is 16. That means 4 times 18. 2 plus 16, 18. So 4 times 18, which is 72 grams. The mass of water obtained from this balance equation is 72 grams. Then what would be the mass of water obtained if we burn 35.25 grams of trilead? Now remember, for the balance equation, the mass of trilead oxide is 685. So it's this 685 that give us this 72 grams of water. It's 6 lead tetraoxide give us 72 grams of water. Then what will the amount we are using for the experiment give us? That is 35.25 gram of trilead tetraoxide. Let it be X. So that by simple proportion, when we cross multiply this 685 multiply X, that gives us 685X equal to 35.25 multiplied 72 times 72. Dividing both sides by 685, we have 35.25 and then 85. 35.25 multiplied by 72 and divided by 685, that is 3.71. The mass of water is 3.71 approximately. And that answers the question. The next question says, sodium combines with oxygen as follows. What is the mass of oxygen needed to burn 4.6 gram of sodium? Let's make some room on this board. Okay, so sodium combines with oxygen as follows. We have balanced the equation for us. So let's just write it. Na plus O2 gas, giving us sodium oxide solid. Question says, what is the mass of oxygen needed to burn 4.6 gram of sodium? Okay, as it is right now, mass of sodium from the balance equation, let me write that, is very important. From the balance equation, mass of 4 moles of sodium. 4 moles of sodium is equal to 4 times 23. The mass of sodium is 23, and you have 4 mole of it there. And 4 times 23, 92 grams. The question borders on oxygen and sodium. The question says, what is the mass of oxygen needed to burn 4.6 grams of sodium? The mass of oxygen from this balance equation is 32. The mass of O2 from the balance equation is 32 grams, meaning 32 grams of oxygen burns 92 grams of sodium. From this balance equation, 32 grams O2 burns 92 grams of sodium. Then what will burn 4.6 grams of sodium? That will be X. So X gram of oxygen burns 4.6 grams of sodium. So that when we cross multiply this, we have 92 times x, which is 92x, equal to 32 times 4.6. Dividing both sides by 92, 32 times 4.6 divided by 92, and divided by 92, 1.6. 1.6 gram of oxygen is needed to burn what is it? Where is it? 4.6 gram of sodium. The next one says, what volume of oxygen measured at STP will be produced on heating 24.5 gram of potassium triisochlorate 5? That's the question A. Then question B, what is the mass of potassium chloride produced in the reaction? Let's make some room here. Okay. So what volume of oxygen measured at STP will be produced on heating 24.5 gram of potassium triisochlorate? Potassium triisochlorate 5 is KClO3. And when you heat it up, it decomposes to give us potassium chloride and oxygen as a gas. So heating up this potassium triisochlorate 5 will give us potassium chloride and oxygen. Okay, the equation is not balanced. On the left hand side, we have 3 atoms of oxygen. On the right, we have 2. So how do we balance that? Let's start by converting this odd number of atom on the left to even by placing a 2 here, which makes the oxygen to be 6, potassium 2, chlorine 2. We also put 2 here. And then, since we are looking for 6 atoms of oxygen, we put a 3 here. 3 times 2, 6. And so the equation is balanced. And the question says, what volume of oxygen measured at STP will be produced on heating 24.5 gram of potassium triisochlorate 5? The question is on oxygen being produced from potassium triisochlorate. So the question borders on this and this, and it's asking for the volume of oxygen measured at STP. Now at STP, 1 dm cube, 1 mole rather, at STP, 1 mole of any gas occupies a volume of 22.4 dm cube. And that's the standard. As long as it's STP, that is standard temperature and pressure, 1 mole of a gas, we always have this volume. Now from this balance equation, you can see that 2 moles of potassium triisochlorate 5 gives 3 moles of oxygen, and 2 moles of KClO3, 3 moles of oxygen, 3 moles of oxygen. That means 2 moles of this potassium chlorate is giving us 3 times 22.4 dm³ of oxygen. Why is it so? Because we said that 1 mole of any gas has a volume of 22.4 dm³. But in this reaction, the reaction produced 3 moles of oxygen. So that will be 3 times 22.4 dm³ of oxygen from this balance equation. But the question says, what will be the volume if this mass here, 24.5 gram of potassium, is heated? Now we need to know the number of moles in this 24.5 gram. The number of moles is a reacting mass over molar mass. The number of moles is equal to reacting mass over molar mass. But what is molar mass of potassium chlorate? That is, potassium is 39, chlorine is 35.5, oxygen is 16. That will be 16 times 3, since you have 3 atoms in, which is 39 plus 35.5 plus 48, 122.5. Now, we are not using this 2 because this 2 is for this reaction, this balanced reaction. What we are trying to do is to get the number of moles from this very mass here, which has nothing to do with this balance equation. So the number of moles, therefore, in this case, is equal to the mass, which is that 24.5 gram of potassium chlorate divided by this molar mass of potassium chlorate. 24.5 divided by 122.5, 0.2, meaning this mass given to us, the number of moles there is 0.2. So if from the balance equation, we are having 3 times 22.4 dm³ of oxygen, that is 2 moles is giving us, what would this 0.2 mole give us? Since it is 0.2 mole that we are using for the reaction. So let me rewrite that 2 moles here again. 2 moles from the balance equation give us 3 times 22.4 dm³. That means 0.2 mole will give us x. So when we cross multiply this, 2 times x is 2x, equal to 0.2 times 3 times 22.4. X therefore is 0.2 times 3 times 22.4 divided by 2, and divided by 2, 6.72 dm³ of oxygen will be the volume of oxygen produced. And that is question A. Now question B says, what is the mass of potassium chloride produced in the reaction? This one now, mass of potassium chloride produced in the reaction. First of all, we need to get the mass of this that give us this. Then we can get the mass that this one will give. Let's make some room on the board. So from the balance equation, molar mass of mass, 2 moles of potassium triacylchloride 5 is equal to 2 times 39 plus 35.5 for chlorine plus 16 times 3 for oxygen. Everything here is 245 gram. That is the mass of these 2 moles of potassium triacylchloride 5. Then we need to get the mass of this potassium chloride also. Mass of 2 moles of potassium chloride equal to 2 times 39 plus 35.5, which is 39 plus 35.5 times 2, 149 gram, meaning 245 gram of potassium chlorate give us 149 gram of potassium chloride. And what would this 24.5 gram give? Let it be X. So 24.5 gram of potassium chlorate will give us X gram of potassium chloride. So when we cross multiply this, 245 times S is 245x equal to 24.5 times 149 divided both sides by 245, have 24.5 times 149 divided by 245, 24.5 times 149 and divided by 240, 14.5. And the mass of potassium chloride is 14.5 gram. At 14.9, the next one says if 3.15 gram of mercury oxide are thermally decomposed to mercury and oxygen, one mass of mercury will be produced. How many oxygen molecules will be produced? Let's get some room here. Mercury oxide is HgO, and it says thermally decomposed to mercury and oxygen. That is, it is heated and then it decomposes to mercury and oxygen gas. Mercury is, oxygen is 2 here, but on the left hand side it is 1, meaning the equation is not balanced. So let's start by making this oxygen on the left hand side 2, and that affects mercury also. So we need to put 2 here to balance the equation. And now the question says 3.15 gram of mercury oxide are thermally decomposed to mercury and oxygen. What mass of mercury will be produced? And from this balance equation, mass is equal to 2 times mercury is 208, that is the atomic mass. Oxygen is 16. 208 plus 16, that is 224, multiplied by 2, 448 gram. The question borders on what? Mercury oxide and mercury itself. So we need to get mass of this mercury. Excuse me. Mass of 2 moles of mercury, that is 2 times 208, which is 416. Meaning from the balance equation, 448 grams of mercury oxide give us 416 grams of mercury. Then what would 3.15 gram give? 3.15 gram of mercury oxide will give us X. Solving for X, we cross multiply. 448 times S is 448S. Then 3.15 times 416. Dividing both sides by 448. We have 3.15 times 416 divided by 448. Divided by 448. That is 2.93, approximately 2.93 gram of mercury. And the second part of that question is how many oxygen molecules will be produced? How many oxygen molecules will be produced? From the balance equation, 1 mole of oxygen is produced. That's 1 mole from, what is the mass of mercury oxide here is 448. So 448 gram of mercury oxide give us 2 moles of oxygen. Then what will 3.15 give? Let's do that. 448 mercury oxide gives 1 mole of oxygen. Therefore, what is the mass given in the question? 3.15 gram. 3.15 gram of mercury oxide will give X mole. By proportion, X is equal to 3.15 times 1 mole divided by 448. So 3.15 times 1 over 448, which is 3.15 divided by 448. That is 0.007 mole. But the question says molecule, it didn't say mole. The question says molecule of oxygen. Look at the question. See how many oxygen molecule will be produced. What we have there is mole. Mole and molecule are not the same thing. We call that 1 mole of any substance, 1 mole of any substance contains 6.02 times 10 to the power 23 molecule or elementary entity, depending on the type of substance in question. So in this case, we are talking about oxygen molecule now. So the elementary entity should be molecules. So 1 mole of oxygen contains 6.02 times 10 to the power 23 molecules. Therefore, 0.007 mole will contain 0.007 times 6.02 times 10 to the power 23. 0.007 times 6.02 is 0.0442. 0.042 times 10 to the power 23. Expressing this in a perfect standard form, I'm moving the decimal point 2 decimal places. So this becomes 4.2 times 10 to the power 21 molecules. And the next one says chlorine can be prepared by the equation MnO2 plus 4HCl plus NnCl2. I think there's an issue here. There's supposed to be an arrow there instead of plus plus plus. So let's make some room here on the board. MnO2 solid plus 4HCl aqueous, giving us MnCl2 plus Cl gas. This one is aqueous and plus H2O, that is water. Okay, the equation We put two here to balance water. Okay, it's balanced now. Okay, so what the equation want us to do? We say chlorine can be prepared by this very equation. Calculate the mass of hydrochloric acid required to react with 25 grams of manganese oxide. The mass of hydrochloric acid. First of all, let's get the masses from the balance equation. So from the equation, mass of 4HCl is equal to 4 times H is 1, then chlorine is 35.5, which is 4 times 36.5. 4 times 36.5 is 146. Now, question says we have to calculate the mass of hydrochloric acid required to react with 25 grams of manganese oxide. Okay, we also need to get mass of manganese oxide from here. So the question borders on this and this. So mass of manganese oxide is equal to manganese. What's the atomic mass of manganese? It's not given. It's like I did not complete that question. Usually, question like this, the masses of each of the individual atom is given. The manganese is 55. So this is 55 plus oxygen is 16 times 2, which is 55 plus 32. And that will be 87. So from the reaction, 146 gram of HCl react with 87 gram of manganese oxide. 146 gram of HCl react with 87 gram of MnO2. Then what would the question says? Calculate the mass of hydrochloric acid required to react with this. So S gram HCl will react with 25 gram of manganese oxide. 25 gram of manganese oxide. So that when we cross multiply this, x multiply 87, which gives us 87x equal to 146 times 25. 146 times 25. Dividing both sides by 87, s is 146 times 25 divided by 87, which is 146 times 25 and divided by 87, 41.9, 41.95 grams. That is the mass of HCl that reacted with 25 grams of manganese oxide. Question A. Question B says the mass of chlorine gas produced by the reaction, that is by the reaction of this 25 grams of manganese with HCl. First of all, we need to get the mass of chlorine gas produced from this balance equation. And what are we reacting in this case? We are reacting 25 grams of manganese. But from this balance equation, how many grams of manganese produce how many grams of DCl2 here? So mass of manganese from the balance equation is 87. And manganese oxide, not manganese. So let's do that here first. Okay, so as I said, from the reaction, we calculated the mass of manganese oxide in this balance equation, it is 87. Now, mass of chlorine, this is 2 atoms of chlorine. Here, the mass of chlorine, Cl2, is 35.5 times 2, which is 71. Meaning, these 87 grams of manganese oxide in the balance equation give us 71 grams of chlorine. The 87 grams of manganese oxide produces 71 grams of chlorine. Then what would this 25.0 gram produce? 25.0 gram of manganese oxide. Let it be X. Let it produce X gram of chlorine. So when we cross multiply this, 87 times X, 87X, then 25 times 71. So dividing both sides by 87, 25 times 71 divided by 87. We have 71 there. And divided by 87, 20.4. So the mass of chlorine that we produce is 20.4 gram. And the next one say 25 gram of impure calcium trihydrocarbonate 4 react with excess hydrochloric acid, liberating 4.26 dm cube of carbon 4 oxide measured at STP in cube. Well, can do anything there. Okay, so 25 gram of impure calcium trihydrocarbonate 4 reacts with excess hydrochloric acid. Calcium trihydrocarbonate 4, the solid, react with hydrochloric acid. That is going to give us calcium chloride, aqueous, plus water and carbon dioxide. Carbon dioxide gas, then water liquid. Okay. Now, is the equation balanced? Let's do atom count. Calcium 2 on the left. Calcium is 1 on the left, 1 on the right. Now, carbonate has splitted to give us carbon dioxide and 1 molecule of oxygen. So it's balanced. Hydrogen 1 on the left, 2 on the right. Chlorine 1 on the right, 2. So we need to put 2 here to balance the hydrogen and the chlorine. And the equation is balanced. So the question borders on, where is my thought also? It borders on what? Calcium trioxocarbonate 4 and carbon 4 oxide. We need to calculate the mass of calcium carbonate in this balance equation. So from the balance equation, mass of calcium carbonate is equal to calcium is 40 plus carbon is 12, oxygen is 16 times the 3 atom. So 40 plus 12 plus 48, which is 100. Any 100 gram of calcium carbonate reacts to liberate 4.26 dm3. Let's first of all get what is it called? The mass of calcium carbon 4 oxide, not calcium. The mass of carbon 4 oxide. Okay, so in this case, since from the balance equation, 1 mole per gram of calcium carbonate produces 1 mole of carbon 4 oxide, and 1 mole of carbon 4 oxide has a volume of 22.4 dm3. So the question borders on volume. Look at what is given here. Say liberating 4.26 dm3 of carbon 4 oxide. That is when this impure one is burnt. What we are calculating here is from the balance equation. From the balance equation, 100 gram of calcium carbonate give us 1 mole of carbon 4 oxide, and 1 mole of carbon 4 oxide has a volume of 22.4 dm3 at STP. That is the volume. Then what would this 23 gram of impure salt or this impure calcium carbonate, what will it give us? Okay, they give us 1 volume of oxide that is produced by burning this. In other words, we need to know this is impure. They say 23 gram of impure. This mass here is the mass of the impure calcium trioxocarbonate. We can't use that in our calculation because this mass, impurity is part of this mass. And remember that impurity will not react. So we can't use that. That is why they ask us to calculate the percentage purity. So now that we know that 100 gram of calcium carbonate in this balance equation will give us 1 mole of carbon 4 oxide, which is equivalent to 22.4 dm3. Now, what mass within this 23 gram, what mass of calcium carbonate will give us this 4.26 dm3 of carbon 4 oxide? 4.26 dm3 of carbon 4 oxide. Again, why are we not using this 23? This 23 is the mass of the pure salt. In other words, the impurity is part of this mass here. The impurity cannot react. So we cannot use this as our reacting mass. We need to know the actual pure substance that reacted. But they have given us the volume of carbon 4 oxide that is released as a result of the reaction. So we need to know, okay, what is the pure substance that react out of this that produce this 4.26 dm3 of carbon 4 oxide. So in this case, x equal to, as I cross multiply now, x times 22.4 is 22.4x equal to 100 times 4.26. So that's x equal to 100 times 4.26 divided by 22.4 and divided by 22.4, 19.02 approximately, 19.02 gram. That is the mass of the pure salt that reacted. So within that 23 gram of the pure salt, the pure one is 19.02 gram. And the question asks us to calculate the percentage purity of the impure salt. Percentage purity is mass of the pure salt divided by mass of impure multiplied by 100. I hope you get the logic. Impurity cannot react that two together. So within that, the reaction occur with the pure, and the value is 19.02 gram. Now that we know the mass of pure, percentage purity is equal to mass of pure substance over mass of impure substance times 100 over 1. Mass of pure salt, that is 19.02, divided by 23, that is the mass given in the question, that is the 23, multiplied by 100 over 1. 19.02 times 100, then divided by 23, 82.7%. The percentage purity is 82.7. And the last one, it said calculate the mass of sodium triisocarbonate 4 produced by the complete decomposition of 16.8 gram of sodium hydrogen triisocarbonate 4. Let's make some room here. First of all, the equation of reaction, sodium triisocarbonate 4 produced by what? The complete decomposition of sodium hydrogen triisocarbonate 4 decomposes to give sodium carbonate and water and carbon dioxide. Okay, sodium carbonate, so there's a 2 there, I omitted it. The sodium carbonate plus water plus carbon dioxide. Now, is the equation balanced? It's not balanced. On the left-hand side, you have one atom of sodium. On the right, you have two. Let's start by putting two there. Also, hydrogen 2, yes. Then carbonate. We use carbonate split up to give, we have, let's do atom count instead. Carbon, two atom there. Also two here. There's one carbon here. There's another one here. Then oxygen altogether on the left is 6, 3 here, 2 here, that is 5, plus this 6. Okay, the equation is balanced. Now the question says we should calculate the mass of sodium triisocarbonate 4 produced, that is this one here, by the complete decomposition of 16.8 gram of sodium hydrogen. Okay, so the question borders on this and this. So from the balance equation, mass of sodium hydrogen carbonate is equal to sodium is 23, hydrogen is 1, carbon is 12, oxygen is 16, then times 3, which is 23 plus 1 plus 12 plus 48. That is 24 plus 12, then plus 48, 84. So the mass is 84 gram. The mass of sodium carbonate, sodium is 23 times 2, and plus carbon is 12, plus oxygen is 16, times the 3 atoms, that would be 46, 46 plus 12 plus 48, which is 106 gram. Meaning from this balance equation, 84 gram of sodium hydrogen carbonate. Okay, it's actually 2 moles of it. I omitted that. The mass of 2 moles of this, that will be 2 times this, or 2 times this, and 2 times 84. That should be 168. Sorry. 2 times 84, yeah, 168. This is supposed to be 168 gram. Okay, from the balance equation. So therefore, 168 gram of sodium hydrogen carbonate yields 106 gram of sodium carbonate. So if that is the case, then what would this 16.8 gram give us? 16 hydrogen carbonate will give X. Calculating for X by cross multiplying these values, 168 times X is 168X equal to 16 times 16.8 times 106. X therefore is 16.8 times 106 divided by 168. 16.8 multiplied by 106 and divided by 168, which gives us 10.6. So 10.6 gram of sodium carbonate